video covers Griffiths E&M section 1.2.4, the divergence of a vector. Like I mentioned previously, the del operator can be used to take the dot product of a given vector, and that dot product has a particular name. It's called the divergence. So I have my del operator, which I will again define as the unit vectors times, that's an error, times the partial derivatives in particular directions. And I can take the dot product of that del operator with some vector. Let's call that vector v. All right, and this v vector I'm going to say is just a vx in the x hat plus vy in the y hat plus vz in the z hat. So that dot product then looks like, before I distribute anything, dx, dy, dz, dotted with vx x hat plus vy y hat plus vz z hat. Then you take the dot product, you take the product of the like components. So all of my x hats combine, my y hats combine, and all of my z hats combine, and I'm left with a scalar that is d vx dx plus d vy dy plus d vz dz. Now, I emphasize again, the dot product, or the divergence, generates a scalar. Let's get some intuition about what this divergence means. All right. So I like to think about the divergence in terms of a fluid flow. Okay. So if I have some vector field v where I have an accumulation of material, say some air or fluid or whatever, that divergence will be negative. If I have a region where I am losing material, that divergence will be positive. And if I have a region where I am not accumulating or losing material, that divergence will be 0. So given that, let's look at the field where I'll call this the z hat direction. I have a vector field that is constant along other directions, but is getting bigger as I go in z. All right. I am losing material as I go in z, and I'm not accumulating any material as I go in any other direction. So I would expect that I would measure a positive divergence, a contribution to the divergence that is positive for the z direction and no other components in any other directions. That is example 1.4 VC. That's the third example. That vector field VC is just z in the z hat direction. Let's go ahead and calculate the divergence of that vector field. So that is x, right? That is d vx d x plus d vy dy plus d vz dz. All right, there is no components of vx and vy. Those are zeros. We didn't write them, but they're zeros. So I'm only left with the contribution from vz. The derivative of vz with respect to z is equal to 1. So no contribution in x and y like we expected, and some positive contribution from z as we expected here.